When we interact with a modern AI agent, it feels like tapping into a unified digital mind, something that listens, adapts, and responds in real time. We open a clean chat interface, type a question, and get a thoughtful answer back. It feels like a seamless conversation with a single entity. But that smooth conversational back and forth is an illusion. There is no single brain doing the thinking. The software is executing a strict set of mathematical parameters. What you are actually interacting with is the final output of a massive 4-stage engineering pipeline: pre-training, reasoning RL, post-training, and prompting. To understand how this system actually operates, we have to look past the chat window and track how engineers allocate data and compute power across these 4 stages. The entire system relies entirely on the heavy lifting done in the very first stage, a stage that behaves nothing like the polite assistant you talk to. Moving up the pipeline, data and costs plummet. Pre-training needs 10 trillion words and $10 million. Reasoning RL takes 1 million problems and dollars. Post-training requires tens of thousands of examples and dollars. Prompting takes 0 data and 0 cost. As the model gets closer to human alignment, the engineering bottleneck shifts. It stops being a problem of raw server costs and becomes a problem of figuring out what human evaluators actually want. Because almost all the capital and computing power is burned on that massive pre-training foundation, that is where we need to look to understand how the machine actually works. The entire goal of that $10 million pre-training stage boils down to a single mechanical task: teaching the model to predict the next word on the internet. This is a familiar concept. If you open a new text message on your phone and start typing, your keyboard automatically suggests the next logical word. Massive artificial intelligence models do the exact same thing. They are autoregressive language models, and they run on a continuous 5-step loop. Step 1 is tokenization. Your input sentence is chopped into mathematical tokens. Step 2, the forward pass. Tokens enter the processor to calculate what comes next. In step 3, the system outputs a probability distribution, assigning a percentage chance to possible next words. Finally, in steps 4 and 5, the model selects one of those words based on its internal parameters and translates that mathematical token back into readable English. The loop itself is simple. The multi-million-dollar engineering challenge lies entirely in step 2, how the forward pass actually calculates those probabilities accurately. So how does a machine actually learn the statistical probability of what word comes next? Historically, engineers relied on a naive statistical method called n-grams. Instead of complex artificial intelligence, n-grams used a straightforward counting database. The equation calculates the probability of a next word by dividing the count of the exact sequence by the count of the base phrase. To guess what follows "the grass is," it scans Wikipedia, counting every appearance, and tallies how often it ends with green. This creates a fatal denominator problem. The computer must keep an exact count for every single word combination in existence, but language creates a combinatorial explosion. The vast majority of sentences generated by humans are mathematically unique and have never been written down before. When an n-gram model is fed a novel sentence structure that it hasn't explicitly tallied in its database, the probability drops to 0, and the prediction engine stalls out completely. A rigid counting database cannot generalize language. If we want a machine to hold a dynamic conversation, explicit tracking is structurally useless. That combinatorial explosion of unique sentences is exactly why engineers had to invent neural network architectures for language modeling. Neural networks bypass explicit counting entirely. Instead of maintaining a database of sequential tallies, they learn fluid, abstract relationships between concepts. By forming these generalized representations, the model can accurately predict the next word, even when placed in an entirely novel context it has never seen before. But there is an engineering catch. To build those accurate representations without relying on hard counts, the neural network requires an incomprehensibly vast dataset to learn from. Solving the microscopic mathematical failure of n-grams is the exact catalyst that forces the pre-training stage to scale to extreme sizes. Back to the macro scale. To generalize human language, the pre-training tier's scale must be immense. Tech companies scrape over 20 billion web pages. This text is chopped into 10 trillion tokens, continuously passing through the autoregressive loop. Processing this volume of data takes months of continuous runtime on massive server farms, driving the upfront cost into the tens of millions of dollars. Teaching a model everything in the world via next word prediction is not magic. It is a brute force computational engineering task. That massive, unaligned statistical engine is a far cry from the refined assistant you interact with on your phone. When asking a chatbot a question, its thoughtful response isn't a distinct personality. You're looking at the final, polished layer of the pipeline. The top 3 stages, reasoning RL, post-training, and prompting, do not teach the model language, and they do not teach it facts about the world. Instead, engineers use tiny amounts of data in these final stages to steer and restrict the statistical engine, fine-tuning outputs to maximize human preference. The sophisticated reasoning of an AI agent is an emergent property, the result of solving a microscopic probability problem at a planetary scale.